So this is the second class for our circular motion and gravitation chapter from the A2 syllabus. In our last class, we developed a couple of ideas. We saw that the angle of an object can be of a circular motion object can be given by s equals to r theta, and we also defined that angular velocity or angular speed omega can be given as theta over time, which can be also written as 2 pi over time period, or it can be also written as twice pi into frequency of the object. We have seen how to convert RPM into omega. So in radian per second, we saw that. As for the formula part, we have also seen that angular centripetal acceleration is given by v square divided by r, which can be also written as omega square r. So this is the same formula for the centripetal acceleration. And what we have also seen that the centripetal acceleration of an object centripetal force can be given by mass into acceleration. So in that case, if we just replace the value of a over here, we can write this as m v square by r, or we can also write as m omega square r. And one more additional thing, that for circular motion object, the velocity of the object would always be perpendicular to the force of the object. And because this relationship always going to hold true, the net work done at any point of time would be 0, because there is no motion or displacement happening in the direction of the force. So these are the basics that we have established in our last class, and in today's class we're gonna see some of the parts how we can use these things for the case of gravitational forces. So if we go for the first thing of gravitation chapter, the first thing is very simple. Gravitational force was first discovered by Isaac Newton, the big and famous incident of the apple tree and stuff. And what Isaac Newton to give us the formula how to measure the gravitational force between multiple objects. One of the key aspect that I want all of you to understand, which many of you know from your AS practices as well, is that whenever we're going to discuss a certain scenario with the necessary components attached to it, it is important that you try to visualize that scenario as an isolated system. Isolated system means, let's say, if I try to tell you that, let's say, there are two objects, mass, let's say m1 and m2, which are separated by a distance of, let's say, r, from their center to center. I want you to visualize these two objects to be the only two objects in your observation region. So try to visualize a void, an empty space with nothing around, and within that empty space you only have these two objects, and you're going to try to decipher how these two objects interact with each other because of their masses or other incidents that we're going to talk about. This really helps for you to get rid of the other typical problems of the world. For example, naturally, if you try to visualize that there are two objects in space, but you try to visualize that there is a ground underneath, then they will be affected by their own gravitational pull. They'll be also affected by the gravitational pull of the Earth, which is an added unnecessary complication that we do not want to include for our discussion right over here. So it's important when you are visualizing the scenarios for different topics, try to visualize an isolated system where the objects discussed are the only objects involved. This would really help to minimize problem and difficulty for understanding as well. So as it tells us that whenever two objects are going to be having masses of, let's say, m1 and m2, and they are in between center to center distances, let's say r, for the sake of convenience, we're using spherical objects. Why are we using spherical objects? I'm going to talk about that in just a little bit. Give me a bit of a time. And the force, the gravitational force that these two objects are going to experience between each other is going to work through a straight line that joins their centers. So if this is a line, I mean, I'm writing this line in dotted line because the force would not be actually seen as a physical line, but the force would be attractive in nature, so they would be pulled towards each other. And let's say that force is given as if g in this case I'm writing this I'm writing this G for to represent this for gravitation. So Fg is the gravitational force which is going to be pulling these two objects together towards each other. So Isaac Newton tells us two proportionalities. He says that the pull of gravitational force is going to be directly proportional to the product of M1 and M2 is going to be inversely proportional to the square of the distance. Now, I'm pretty sure he came up with these proportionalities by some sort of experimentation. I do not actually know the historical background how he came up with these proportionalities, but uh, as it happens, this proportionalities has been found correct and has been found to be exactly accurate over the long duration since Isaac Newton has given us this formula, and they are actually correct information. If we now combine these together, these two proportionalities together, we can write this combined proportionality. Fg is proportional to m1 m2 divided by r squared. This is the combined gravitational relationship. If we want to convert this into a constant, we're going to replace this with a proportionality constant. And for the case of gravitational rule, we actually give the constant, which is the capital G, other than using a K. I'm going to talk about this in a bit. M1, M2 by R square. G is what we call the universal gravitational constant. There are not so many universal constants that we know, but gravitational constant is said to be gravitational constant. This constant is said to be a universal gravitational constant because this is a constant that is same in all of our known universe. All of our known universe, I'm using the term known because much of the part of the universe is still unknown to us human beings. The observable universe that we see, where we can actually observe the mass and the energy that we know as, they are visible objects, but there are also dark matter and dark energy, which effect we can see by the bending of light and other incidents, but we haven't actually experienced those things in physical measurable terms. চর্মচক্ষু দ্বারা আমরা এখনো সেগুলোকে সেন্স করতে পারি নাই, but couldn't be justified or couldn't be detected by our physical senses. So one hypothesis for the dark matter, I'm talking about dark matter a little bit because this is something very interesting for the scientists, and this is one of the key research part for the astronomy sciences currently around the world. One of the hypotheses which really sounds logical to me is that objects can actually exist in a lot of more dimension than the three-dimensional object. For example, we experience a three-dimensional world which moves through the fourth-dimension time. We can have two-dimensional objects which have lengths and widths, which can be, let's say, a surface, which you experience its movement in a three-dimension. For example, let's say height. So there can be multiple different multi-dimensional objects moving through another dimension. But irrespective of all of those dimensional objects, mass of objects is a certain property that penetrates through or what is this word? Transpire or transfer, not transpire. No. It actually goes through all the dimensions. Mass of objects, whether it's a two-dimensional being or three-dimensional being or four-dimensional being or n-dimensional thing, mass of objects is a fact that can be understood from all dimensions. Mass is an its effects can be seen everywhere. So one of the hypotheses, not proven hypothesis, that the other dark matter and the dark energy that we cannot see might be coming from four-dimensional or five-dimensional beings, which we cannot perceive because we are only three-dimensional beings. So, but we can see their effect because light or electromagnetic waves are seen to bend or behave differently than our prediction in many of the cases. Anyway, so universal gravitational constant for our known universe, this G has a constant value everywhere, and at this point we're going to try to define how this G works. G is actually, if we subject the constant G from this equation right over here, this is going to look like F into R square divided by M1 into M2. The way we define this constant G is by making the measurable quantities R and M1, M2 as unit. So what we say that if we have two objects, each of which are 1 kg, So we have two 1 kg objects which are separated by exactly 1 meter. So try to understand this part. Two 1 kg objects separated by 1 meter, which means in this case for this equation we are trying to replace this one as 1 kg, so unit mass, this one as 1 kg unit mass, and this distance as 1 meter or unit distance. So and in that case the amount of force, gravitational force, by which they will be pulling each other is, this is the force. This amount of force is defined numerically as the universal gravitational constant. So if I just place all the numbers over here, other than the unit, let's say I'm going to write F into 1 squared divided by 1 into 1, ultimately we get F. So the definition of universal gravitational constant goes like this. I'm not going to write this, but I'm just saying it slowly so that you can grasp the idea. The amount of force by which two objects attract each other due to gravitational force when their masses are 1 kg each and they are separated by exactly 1 meter distance is called the universal gravitational constant. I'll say it again. The amount of gravitational force between two objects, both of which are 1 kg each and they are separated by a distance of exactly 1 meter, is said to be universal gravitational constant. So universal gravitational constant is basically defined as the force that exists between two 1 kg objects which are separated by exactly 1 meter distance. এই ডেফিনিশনটা বোঝা গেছে কিনা বলবান?
জি স্যার।
সো এটা গেল ইউনিভার্সাল গ্র্যাভিটেশনাল ফোর্সের কনস্ট্যান্ট। এখান থেকে যদি আমরা ইউনিট থেকে ডিরাইভ করার চেষ্টা করি, সো এখান থেকে the unit of this universal gravitational constant can be obtained from this expression. Let me use a different color maybe. So if I go from here, G would have an unit of Newton meter square per kg square. By repeated and different designs of experiments, the value of G has been all around accepted as had to have a constant value of 6.67 into 10 to the power minus 11 Newton meter square per kg square. You don't have to memorize this value. You just have to understand that this is a really small number, which means if two 1 kg objects are spaced is separated by only 1 meter distance between each other, they are gonna attract each other by only virtue of gravitational force. The attraction between them is gonna be 6.67 10 to the power minus 11 Newton. So this is a pretty small force. Measuring this one small force can also prove to be very difficult, but scientists had reliable ways where they could subtract or they could disregard or discard the effect of other type of attraction forces. For example, if there are some sort of electrostatic attraction force or some sort of van der Waals attraction forces, they could get rid of those effects and could exclusively measure the force due to gravitational pull. So that's the value, and this will be available to you in the formula sheet. Let me just assure you on that part so that you don't have to bother to memorize this thing. I could pull up any of the question papers. Says 19, paper 4. If you just dive into here, you can see that there you are. Gravitational constant capital G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. So you don't have to bother to memorize this. For reasons unknown, I don't know why. In some of these expressions, the multiplication sign is given. In some of them, this is missing. This is pretty common in many of the CIE papers. I don't know what happens with their multiplication sign, but you do understand. You should understand that in each of these gaps, there exists a multiplication sign before the tens power. Weird, but workable. So that's the preliminary idea for gravitational constant and Newton's gravitational law. The next topic that we cover in this chapter is what we call gravitational field strength. Gravitational field strength. Okay, before I'm going to define gravitational field strength in a bit, but I just told you a little bit earlier that whenever we are trying to describe the Newton's gravitational law, we prefer to use examples of circular or spherical objects. Now, why is that? Why not any different shape? Why not a cylinder, or why not a random piece of rock type of shape? Not the wrestler rock, I mean regular rock. So why don't we use those things? The reason is that when when Isaac Newton actually gave us the law for gravitational force, he actually said that this force exists between two particles. So his statement for gravitational no, let me show you his exact statement, so that you can understand why the sphere is used for the definition. Just a second. Mm, okay, here we go. Newton's law of gravitation, universal gravitation, is usually stated as that. So it starts from this point. Every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So he is using the term, he has actually used the term particle in his idea, in his statement of the law. How do we define? I have to do ad block. Okay, I'll do the ad block. Where is my ad block? There is my ad block. Uh, yeah. Newton's law of gravitation statement that any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. So because he used the idea of particle, the idea of particle is very simple. In physics, the word particle is a bit of an abstract idea. This is something that you have to imagine, although you cannot imagine this. A particle is said to be such a being which has measurable mass but zero dimension. It doesn't have any volume. So it's an existence with mass, but it has no measurable dimension. It's so small that it has zero length, width, or height, but it has mass. It has measurable mass. If you wonder how is that even possible, well, it is not technically possible for us to imagine something like that, because, well, obviously you cannot imagine a thing that doesn't look like anything. If you even try to visualize anything in your head, to be even the smallest of the object, you have to visualize it with some sort of dimension, but the idea of particle states that has some amount of mass, measurable mass, but it has zero dimension. The reason it is actually applicable, because if you consider the distance between stars or celestial bodies from one place to another place, in many cases, not in most cases, I mean, for the distance in between, their individual sizes are extremely small. I mean, I'm not talking about for the solar system. I'm talking about like a really large scale celestial distances. So that's what makes that statement or Newton's law somewhat understandable, that why it should be considered as particles. Another benefit of considering the object as a particle, not mentioning them as three-dimensional object, is that we can get rid of the problem of where the force will work, the adjoining line through which the force will work. I mean, if these things were not considered to be spheres, these things were considered to be exactly particles, let's say very point masses. Point mass is also an idea of particle. Then you would know that by no means the force could work anywhere other than the line that joins these two particles. So the working alignment of the gravitational force would be well defined whenever you define those things as a particle. So in the formula we use the term particle, but for my explanation I went directly for a spherical explanation, spherical shape for my explanation. Why is that? It is because the gravitational field, the shape of gravitational field, which is drawn using field lines, the gravitational field of a particle has a similar orientation like a sphere. This is something very important for you to understand. Whenever we have objects which produce similar field, we can have them replaced in between each other for convenience's sake. Let me elaborate what this means. Before I get into the idea of gravitational field strength, I would like to talk a little bit about gravitational field lines. You kids have learned about field lines in your O levels or in your SSC as well. Uh, Let me just refresh your memory, help you refresh your memories a little bit. I'm actually talking a lot over this process. None of you are raising hands and none of you are asking me questions. So I'm assuming that you are either getting this or this is too boring for you to bother. I'm not sure which one is it. No one is making any comment about that.
স্যার বুঝতে পারছি।
আচ্ছা, okay. Anyone else? I mean, বুঝে যাচ্ছে কি কথা? Should I slow down?
জি স্যার বুঝে
আচ্ছা, ঠিক আছে। The gravitational. Let me help you refresh the idea of field lines or field a little bit. Field lines are imaginary lines which are used to represent the existence and orientation of a field within a certain location. The first thing is that field lines are all imaginary lines. So whether you use gravitational field lines or elliptical field lines or magnetic field lines, they actually do not exist. These field lines are just a way, understandable or easy to understand way for us human beings, for our visualization purpose, that we can use field lines to represent that a field exists in a certain place. And we can also, by the direction of the arrows of the field lines, you can represent in which direction the field works. The field works in many cases might not necessarily mean in which direction the force works. We have to define the fields for our individual purposes. The field lines were first used by Michael Faraday when he was trying to explain the idea of electromagnetic induction thing. Then it was accepted for the electric field case, and then scientists also use this same idea of field to explain the gravitational field as well. So a field is usually defined in physics. A field is usually defined as a region of space where you have some sort of force available. So a gravitational field is a region of space, empty space, where you have such a property that if you bring another mass is the object that experiences gravitational force. Where you bring another, if you bring another mass, it is going to be experiencing a force of pull due to the gravitational field. So field is the region of space where you have some sort of force available. An elliptical field would be a region of space where if you bring another charged object, maybe positive, maybe negative, it would experience a force. It might be repulsive force, it might be attractive force that comes upon two if conditions, same like charges repel and opposite charges attract. But an elliptic field is defined to be the region of space where another charged particle would experience a force. So how do we have those kind of spaces? We only simply have that kind of spaces simply by having mass in a certain location, or simply by having charge within a certain location. So the idea is that if we have I'm going to show you the idea of electric charges a little bit, so which actually is going to be much more vividly discussed in the chapter electric field and capacitors. But I have a reason to bring up Coulomb's law and electric field over here, because pretty soon I'm going to be telling you that gravitational force is a negative force. Now, where does this word negative force comes from? That actually comes from the idea of Coulomb's law, where we also have the involvement of a positive force. So that's why it's important. The way electric field charges are defined is that positive charges, spherical positive charges, or if I just try to draw a point charge, let's say this is a point charge of positive charge, this is a spherical object with positive charge. Let's say their charges are exactly the same. So let's say this is also +1 coulomb, this is also +1 coulomb. Let's assume that they're equal charge, but one is of dimension, another one is of no dimension. If this sphere, let me use black, if this point charge produces a field line of this much, I'm only showing here the field line with only 4 lines to represent that the field is like this. What I'm trying to show you is that this field is an ever extending field, and you have to I'm trying to tell you that these two objects are not affecting each other for the timing. They are free with respect to each other, so they are not related to each other. For the timing, they are not affecting any force onto each other. Consider them as individual objects. I'm going to bring them closer pretty soon, and we're going to see what happens. So if we have these two objects, this object is in space, and if this one produces field lines like this, in this case, what I'm trying to show you is that +1 coulomb charge, the field that is produced by a +1 coulomb charge, is represented by 4 arrows, which are ever extending in infinite towards infinite directions. And as these lines slowly get further away from the charge, the distance between the lines are slowly becoming larger, slowly becoming larger. I'm giving circular, but I could have also given state direction. But what I want to see that the lines are getting further apart from each other as you slowly get further away from the point charge, representing that the field is slowly becoming weak. It just so happens, if we have a metallic sphere which also is charged by a +1 coulomb charge, this would produce an exactly identical electric field around itself as well. So it will also have an electric field of similar strength and similar orientation, except for this part only where the particle itself exists. So beyond this point, let's say if this amount of direction is let's say 1 centimeter, I'm assuming this part. So for 1 centimeter part of spherical region, the field line would not be exactly same because the object actually physically existing there. But beyond that point, beyond this 1 centimeter, this field and this field would work exactly the same. They would appear same in terms of electric field lines. They will exert same amount of force in other charged objects if we bring them close, and their behavior will be exactly same. This is why, for the sake of convenience, in many cases we can have these two objects replaceable with one another. So in cases where using a sphere is convenient for us to explain something, we use the sphere. In cases where the point mass is useful or easy for us to explain something, we go for the point mass, because their ultimate effect of electric field would be exactly same. I use the example for 1 coulomb over here. Let's say if both of these objects were charged by a 2 coulomb charge, +2 coulomb charge, both of them were charged by 2 coulomb each. In that case, simply we're going to have double the field lines. So let's say in that case, I can draw 4 more lines going through their center. So let's say well, now we have 8 lines representing a double strong field line, and same thing over here. So we're going to have more lines coming out and more lines coming out, and we can actually increase the value of the field lines charge and to have a bigger number of electric field lines over here, and vice versa. Point that I'm trying to make is that the shape of electric field and the shape of electric field of a spherical object and of a point mass are of same shape. That's why they can be used replaceably. We can use one alternate to other. Another important thing that you need to understand, that if you might wonder that why is that same, this is same because field lines have multiple different properties. One of the important aspect of a field line is that every field line come out of the object's surface perpendicular to that surface. Important bit, which means if it's a sphere, then as the field line leaves from here, it's going to produce a perfect 90-degree over here. As this field line leaves from here, this is going to produce a perfect 90-degree over here. As this field line leaves from here, this is going to produce a perfect 90-degree right over here, and so on and so forth. If we did not consider a spherical object, rather if we consider let's say a cube object or a perfectly cube object, what's going to happen, let's say this cube object is also charged by +2 coulomb. So it's going to also produce 8 field lines around it, but these 8 field lines are not going to be produced in the same orientation like this. Let's say 4 field lines I can draw pretty easily, like that, like that, like that, like that. But the other 4, I'm going to have a bit of a difficulty to understand, to draw those other four field lines, because at this corner it's going to be pretty difficult for me to draw that exact field line. If you wonder why, if I zoom in on this corner, any corner that might appear to be a perfect corner in naked eye, in blank eye, but if you zoom on in onto the crystal structure of the metal, you would very much find out that the corner is actually not a perfect corner. It has shapes like these for a very highly zoomed in view, and electric field lines would have to come out from somewhere. So if it is actually coming in from this end, it's gonna come out like that, being perpendicular to this. If it is coming out from this side, it's gonna come out perpendicular to that part and eventually go in the other. If it is coming out from here, it's gonna come out perpendicular to this face and eventually bend to become going upright. So it would always make an instantaneous 90-degree angle with the very point from where it is coming out, and then it can take its necessary bending to manage itself with the other existing field lines. That's also possible. But what is really important for you to understand, that for a sphere we pretty much don't have that problem. For a smooth sphere, the surface is by default nearly flat. For just flat means for a small amount of surface on a sphere, we can consider that to be apparently flat, or uh, workably flat. There is a word, approximately flat. Yeah, approximately flat. So the field lines can come out perpendicular to the surface and give us a similar shape for a point object. And that the same thing is applicable for masses as well. Interesting bit, positive charges give us outward field, and negative charges, if we have a point mass which is charged by, let's say, -2 coulomb, uh, negative charges are shown with inward field lines. Negative charges field is shown as negative field lines. You might wonder, how do we define this? I mean, what is the basis on which we actually define this direction? I mean, why are we giving positive outward arrows, and why are we giving inward arrows? I mean, what is the point of it, of a point of all this? The point is very simple. The point is, the behavior of an electric field, hear me out on this one, the behavior of an electric field is defined by the force experienced by a +1 coulomb charge. This is considered as the defining test charge required for an electric field. +1 coulomb, you need positive charge. You might wonder, why you need positive charge, why not you need negative charge? Because you should know that when the scientists were dealing with electricity, and they had to define that something moves from one object to another object to make it charge. Electricity is the flow of charged particles. So by virtue of no physical proof, just because they had to explain something, they assumed, the scientists of that time assumed, that positively charged particles move from one place to another place, and that's how we can have the flow of electricity. But later the scientists discovered the shape of the atom, structure of the atom and the atomic structure, and then they came to understand that, well, positive charged particles slash protons do not move, actually electrons move. But then again, they decided to hang on to the historical mistake and name the whole thing as conventional current and blah 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 blah. So since that point, positive charge was, since at that point of history of physics knowledge growth, scientists decided that positively charged particles actually move from one place to another place. That's what they assumed. And because of that, electric field was also defined by means of the force experienced by unit positive charge moving from one place to another place. So the way charges interact is that like charges repel and opposite charges attract. So if you have if you have a positively charged object located right over here, which is producing some electric field around itself, and if you bring about another unit positive charge, let me draw that with maybe red. Let's say if you bring another unit positive charge over here, let's say that is a +1 coulomb charge, these two things are going to repel each other, and the direction of this force is going to be exactly the adjoining line and then outward. So this is going to be the force experienced by this test positive charge. No matter where you place it, if you place it closer, it's going to experience a stronger force. If you place it farther, it's going to experience a weaker force. If you place it exactly on the field lines, it's going to experience the force exactly along the field line, outwards, radially outwards. If you place it somewhere in between, you can find out the force direction by just joining the point charge and that position and extending the arrow outwards. Although we don't have any field lines over in this gap, it doesn't mean that it does not mean that electric field is unpresent here. Electric field is equally present everywhere. We are only using 8 arrows for the sake of our convenience to represent those existence of the field lines, because drawing an infinite number of field lines with gradually decreasing darkness for a hand-drawn or case would be really difficult. So we prefer to use more or less field lines to represent a strong or weak field. But field is present everywhere. I mean, it's not only present on the alignment of the lines, it's present everywhere. We use those lines to represent its orientation for some very specific lines, and the in-between spaces are assumed to behave in accordance with what we have drawn. So because positive charges actually experience the force outwards, that's why positive charge, the field that is produced by positive charges, this one or this one, those fields have a direction radially outwards. Vice versa, if you have an negatively charged objects in some place and you are about to test the electric field of this one by placing a unit positive charge right over here, it is going to experience a force directly towards the center because opposite charges attract. So because that force is going to work inward, so that's why we define that the negative charges have an inward field, or they have an attractive field. They have a repulsive field, they have an attractive field. What does the this idea of attraction and repulsion come on? The fact that we decided, or we defined, that the behavior of electric field will be justified or will be described upon the movement or the force experienced by unit positive charge. We predefined this logic, and depending upon that, we define that the positive charges field are outwards and negative charges fields are inwards. এই পর্যন্ত বোঝা গেছে কিনা?
Yes, sir.
আচ্ছা, কোনো কোশ্চেন থাকলে বলো, I'll take time to explain stuffs. What happens is, interestingly, for masses is that masses don't have any repulsive property whatsoever. Gravitational force is only found to be exclusively attractive. I'll say it again. Gravitational force is found so far to be exclusively attractive. Gravitational force does not have any repulsive version. I mean, we yet found what is called anti-gravity. No, we didn't. So whenever we have two objects placed, or two masses placed from one to another one, let's say this is a test object that we want to measure the gravitational field for. Let's say this has a mass of m, and we want to measure how much is the gravitational field strength or gravitational field around it. Pretty much similar to this idea, if you try to understand that, because charges can be of two types, plus and minus, we had to define 1 coulomb, and along that amount we also had to define the polarity of plus. But for masses, we don't have positive or negative masses. We have antimatter, but antimatter also has positive mass. Its measurable mass is positive. It doesn't have a negative mass. Antimatter কি জিনিস সেটা তোমরা অলওয়েজ এএসএ কিছু পড়ছো, antiparticles and antimatter. They have every property same like the particle except for their mass. So mass is same, but every other property is absolutely opposite for particle. Anyway, so to observe the behavior for gravitational field, let's say we bring about an object that has a mass of exactly 1 kg. That's the unit mass. What will always happen that this object, by virtue of its gravitational force, will always pull it inward. Always pull it inward, no matter where you place it. If you place it closer, it's going to be a stronger force. If you place it farther apart, it's going to be a weaker force. But the force of gravitation will always pull your test object, namely 1 kg object, towards the motion, which is similar to what is happening to the negatively charged object over here. Now you might wonder that, well, these two are similar, but they're not the same thing. Why are we even bothering to talk about this stuff? Because eventually, whenever the scientists actually work with forces, multiple forces need to be considered simultaneously. Let me show you an example for how does the Coulomb's law work, and then we can go for a little bit of comparison for these two things. Einstein's gravitational law looks like this. Force of gravitation is directly proportional to mass 1 into mass 2 divided by r square, where the two masses are spaced apart by r distance, and the force works along their adjoining line. Coulomb's law, the law that tells us about the force that exists between charge particles, tells us that force between two charge object is directly proportional to the amount of charge of these two objects, q1 multiplied by q2 divided by r square. So if you have two charge objects, let's say one has charge of q1, the other one has charge of q2, and they're spaced up by a distance of r in between their centers, in that case the force that will exist between each other is going to be fc. Now I'm not giving arrow over here because just this force by virtue of charges can be positive, repulsive, or attractive depending upon their type of charge. But here's what I need you to understand. If we can just get rid of the proportionality sign by giving a constant over here, let's say this constant is actually 1 pi 4 pi epsilon naught, but for that, I mean, let's just write it as k, and let's say we're going to write this constant as g. So you have these two constants over here. F equals to g m1 by m2 by r square, and f equals to k into q1 q2 by r square. And what you should understand that in the Coulomb's law, if these two charges are of the same type, try to visualize in your head. If both q1 and q2 are positive, then when you multiply these two, ultimately the force will also be positive. So positive charges gives you positive force. If both of the force charges are negative, then if you multiply minus into minus, you're still gonna get a positive force. You need to understand that like charges repel. So the force, the type of force which is exists between two positive charges, or the type of force that exists between two negative charges, is actually repulsive force, which by equation is coming out to be a positive force. Whereas if the two charges are dissimilar, let's say if they are plus and minus, or minus and plus, if you multiply these two things, you're going to end up with a negative force. This force is, by our understanding, is actually an attractive force. So actually from Coulomb's law, we actually define these two forces, that whenever we have attractive forces, we call them to be negative forces. Whenever we have positive, whenever we have repulsive forces, we call them to be positive forces. Because gravitational force is always exclusively attractive, from this consideration, we say gravitational force is a negative force because it is always attractive. এই কম্পারিজনটা বুঝা গেছে কিনা?
जी sir.
Anyone else? Any question? That why gravitational force is considered to be a negative force? Because it is attractive. And what is this idea of negative comes from? It comes from the idea of Coulomb's law, from the basic idea of multiplication, where we have opposite type of charges, plus and minus, available. But for gravitational force, we don't have plus or minus. We only have mass, which is only attractive. Gravitational force is a negative force. এই আইডিয়াটা আমাদের পরে কাজে লাগবে যখন আমরা গ্র্যাভিটেশনাল পটেনশিয়ালের কনসেপ্টটা দেখব, একটু পরে দেখতেছি সেটা। আচ্ছা, let's get back to the point of gravitational field strength. Where is gravitational field? There you are. So let me just steal this heading. Lambda effect. Gravitational field strength is actually pretty simple. Whenever you are going to come across the idea of field strength, in almost all cases, the field strength is actually divided by force per something. The reason I'm writing it in this manner is to give you a bit more generalized idea. Whenever we're dealing with gravitational field strength, this actually, this one is force per mass, because gravitational force works with masses. If you have electric field strength, which is going to show up in a later chapter, this is going to be force per charge. Now, because charge can be plus or minus, we go for force per unit positive charge. So that's the difference. Field strength in generally means force per something. If it is gravitational field strength, it is force per mass. If it is electric field strength, it is force per charge. We also have a thing called magnetic field strength, or magnetic field intensity, which is gonna come up in the electromagnetism chapter. That is, however, is defined as a different thing, because magnetic behavior does not have monopoles. We don't have a single north pole, or we don't have a single south pole. So magnetic field strength is defined in a totally different way, other than this idea of gravitational field strength or magnetic field strength. Anyway, that's a different story. You will experience this over the duration of this course anyway. So we're going to talk about magnetic field strength in its appropriate place anyway. So the way we define gravitational field strength is this. If we have a gravitational field somewhere, so let's say I'm not going to draw an object over here, but I want you to understand that, let's say within this apparently rectangular bread kind of shaped space, we have some gravitational field. Let's assume that we have some gravitational field existing over here by virtue of some mass nearby. If we place a 1 kg object anywhere within this field, let's say I'm going to place a 1 kg object over here, and this object is going to start experiencing a force due to gravitational field. Let's say this 1 kg object is experiencing a force in this direction that force has a value of, let's say, 2.39 into 10 to the power minus 2 Newton. I'm saying all of this data just by making up in my head. So we have a region of space which has a pre-existing gravitational field within itself by virtue of some other object. And if we bring about a 1 kg object as our test object within this field and place it, we can measure, let's say, that the force of gravitational pull it experiences is, let's say, 2.39 into 10 to the power minus 2 Newton. We'd say the gravitational field strength of this location is 2.39 into 10 to the power minus 2 Newton per kg. That's the value. And the direction of the gravitational field strength is working in this way. So gravitational field strength is actually defined by this formula. G is equal to force over mass. G, small g, is also the generic symbol for gravitational field strength, which we also use for gravitational acceleration on Earth. Not a big deal. It's the same thing, which also gives us F equals to mg. We have known that this to be W equals to mg, weight. One thing is exclusive for you to understand that, let me just, if we just multiply this equation, let me just write those. What you have already learned up to your O levels, the W equals to mg. So what's the difference between F and W? Honestly, there is no difference. We human beings, or the scientists, human beings, ador kore or care kore Earth's gravitational puller ekta alda naam dise. The gravitational pull of Earth is called weight exclusively. Gravitational pull of sun is called gravitational pull of sun. Gravitational pull of moon is called gravitational pull of moon. Gravitational pull of Earth is somewhat exclusively called weight. So if we use the term of weight, unless otherwise mentioned, we always have to assume that we are talking about the object experiencing the gravitational field on the sun, or near the Earth. So W equals to mg, weight equals to m into g is basically the gravitational pull of Earth on any object is given by mass into gravitational acceleration on Earth. But this expression is the actually Newton's second law, is equally applicable for other cases as well. And whenever you use it for other scenarios like other planets, we can simply write F equals to mg, where in this case, this F is the gravitational force. So I might as well write a G subscript. You will see that in many of these cases in your A2 syllabus, as I'm writing all the forces, I'm preferring to give some sort of subscript over here. I always prefer to give them because it helps me to distinguish between them. Actually, I messed up something over here. I wrote the Coulomb's law. Where did I write the Coulomb's law? Where is that? Yeah, exactly. This subscript was not supposed to be FC. I use FC to represent centripetal force. FC, force centripetal. I usually use FE for electrical field force, so I might as well correct that. Not very important for many of you, but it's important for my thinking process so that I do not mess up stuffs within my head. I like it that way. So this is how we define gravitational field strength. Now, if this is the basic idea for gravitational field strength, but if we are trying to give you a more textbook-like view, this is how it works. Let's say we have an pre-existing object of mass capital M, and we bring about a test mass of, let's say, small m, somewhere close to it. These two objects, this is a more textbook view. Let's say these two objects are r distance apart from each other, and because of the gravitational pull between them, they're going to attract each other. So you have to understand by Newton's third law. Remember Newton's third law, this is pulling this one by Fg, this is also pulling this one by Fg. They're both pulling each other by the same amount of force in opposite direction. Newton's third law. However, who is going to move is dependent upon who has more mass or who has less mass. The one that has less mass would be accelerated more or would be seen to move. The one that has more mass would have more inertia and would be less likely to move, or would have a less acceleration and would be seen to be apparently stationary. So which is going to move is going to be defined by Newton's second law, F equals to ma, which is the inertial idea. However, the force is experienced by both of them equally, working in opposite direction. You should not mess it up. They are both pulling onto each other by the same amount of force of Fg, but that same force will produce differently visible effect onto different objects because of the difference of their individual masses. So not to mess it up. So the theoretical idea is that, let's say this object in this case is experiencing a force of Fg. So the gravitational field strength of this location produced by this mass. So this mass. So I'm going to write this as like this. The gravitational, let me just write this. Field strength. Should I name these two objects? Okay, let's say this is object A. This is object B. At location B, produced by object A of is, let's say G at B equals to Fg divided by M. I have a reason to write this whole thing. This big object is producing gravitational field strength on this. It is actually producing gravitational field strength everywhere. The gravitational field is present everywhere around this object. Just because we place our test object over here, we're talking about the gravitational field strength at this location. It is simply a choice of point that we are making in the empty space around the object A, just for the sake of our measurement or for the sake of discussion. You could have placed it anywhere else. Gravitational field is present everywhere around the object, more or less. Closer you have stronger field, farther away you have weaker field. But for this example, we are choosing this point to make our example. So right at this point, the test mass that we are bringing have a mass of small m, and let's say this is the r distance apart point from center to center, and the pull that this object that is experiencing the pull that this object is experiencing because of this massive object has a value of Fg at this point. So we are saying that the gravitational field strength at location B produced by object A. So the field strength produced by this object at this location is given by Fg by M. And here we have divided by the test mass. This same information could be written vice versa. But before I go for the vice versa part, এই এক্সপ্রেশনটা বোঝা গেছে কিনা বা এই লাইনটুকু বোঝা গেছে কিনা? Everyone have a look. হ্যালো, কে যেন চলে গেছে? একটু আগে 8 জন ছিল। না না না, বাবু কই? বাবু কই? বাবু কই? উপরে যাবে? আচ্ছা, হ্যালো, আমার কথা শোনা যাচ্ছে না?
জি স্যার, বুঝতে পেরেছি।
আচ্ছা, I'll take a small break. I'll be back after 5 minutes. তোমরা in the meantime break now অথবা স্ক্রিন দেখো, anything. So we're using the recording after the break. So this is the part that we actually left off, that we defined the gravitational field strength of near the big mass by using the example of a small mass. If we now try to replace the variables of this within this equation, so let's say I'm gonna write the gravitational field over here, so I can write it in this manner. You have to understand that because I wrote the two masses over here, one as, let me use different color, let's say capital M and small m, so the Fg can be written as G mm by r squared. So if I take this equation and replace the value of G, I can write G equals to G m m divided by r squared divided by m. So you're gonna get so altogether G equals to Gm by r square. That's a generic expression for gravitational field strength for any object. So the way we should understand or remember this formula is that if we have an object that has a mass of capital M, the gravitational field strength from the center of this object at a distance of r, in any direction, doesn't matter, at a distance of r, is the gravitational field strength at this point is given by G equals to gm by r square. That is the generic formula for gravitational field strength for our case. That's another important thing. And then we have a bit weird concept which is called gravitational potential. Gravitational potential নিয়ে আমি এটা আলাপ করতেছি। Gravitational potential একটু weird কেন সেটা আমি তোমাদেরকে এখনই বলবো। এটা একটু কেয়ারফুলি বোঝা লাগবে, নাইলে পরে প্যাচ খেয়ে যাওয়ার পসিবিলিটি আছে। ওকে, gravitational potential সিগন্যাল হচ্ছে phi. Phi হচ্ছে দেখতে এরকম, it's a circle with a vertical line. Let me just show you how it looks like in typed form. Your net 9. হ্যালো, আমার কথা কি শোনা যাচ্ছে?
জি স্যার, শোনা যাচ্ছে।
তো নেট এত স্লো কেন? What? Oh no. What is this? This is weird. ব্রাউজার বলতেছে আমি অফলাইন, পিসি বলতেছে আমি অনলাইন। জুমেও কথা শোনা যাচ্ছে, রাইট?
জি স্যার।
জি স্যার, clear।
আজব। আচ্ছা ঠিক আছে, maybe browser has gone rogue somehow. Anyway, so gravitational potential has a symbol of phi. It is actually a circle with a vertical line that goes through on both sides, not halfway through. Not to mix up this with Ori. Ori is the angled line. This is used to represent empty set in the discussion of set theory, and phi has a vertical line, so you should not mess this up. So I'm gonna get it off so that you don't feel confused. Gravitational potential is conceptually a bit weird. I'll tell you why it is weird. First, I'll start discussing with the idea of potential energy. Let's say this is Earth. This is the Earth surface. Figure not drawn to scale. Let's say we have an object right over here, somewhere above the Earth's surface. Here's a height. So we're going to have some amount of GP of this object stored within this object. As we're going to slowly go up, if we start to move this object further away, so if we slowly go away from the Earth, for what I'm trying to say is that if this is the Earth's surface, let's say this is the center of the Earth, so the distance from the center to center was, let's say, this much. If I start to lift up the object, its GP will increase, right? The farther we take it off the ground, its gravitational potential energy will increase because we have to work against the pull of the gravitation. This is the important bit. Whenever we work against a pre-existing force, energy is stored. When the pre-existing force works by its own, energy is released. কিরকম? মনে করো এই যে এক্সাম্পলটা, এখানে when the object is right over here, it has the weight working downward. This is the Earth's surface. If we want to lift it above, we have to work against this force, and we have to make the separation between the Earth and the object further. That will store bigger amount of GP within that object. The further we're going to take it out away, the more energy we're going to store. This is the very basic core concept of GP. এটুকু তো তোমরা জানো, right? I believe you do. Now come to the idea. Let's say we have a spherical object over here, very large object. Let's say it has a mass of m, center right over here. Let's say we have an object over here, and we're going to at this point this object has some energy, and if we start to slowly take it further away, let's say this object has a mass of m, and if we slowly start it further away, the gp of the object is going to slowly increase and increase and increase. Let's say eventually we take the object at infinite distance. So let's say this much distance is r, this much is r, and let's say this much distance is infinite distance. So ideally speaking, at infinite distance, the amount of energy stored within this object should be maximum, because that's the biggest distance you can separate the two objects at. But the interesting enough, if you consider the formula of gravitational force, let's say Fg is given by g m m by r square. If we replace the r as infinite over here, what are we gonna get? On the denominator side, you get an infinite squared. Although it's mathematically not so proven, but you do understand that whenever we have infinite sign at the denominator, the whole thing practically becomes zero, right? If you divide something
Yes, sir.
by a very, very large number, you actually get zero. What this tells us that when these two objects, m and m, capital M and small m, these two objects will be infinitely spaced, or the distance between them are going to be infinitely large. At that point, the gravitational force of attraction between them is going to become zero. If gravitational force doesn't exist, then gravitational potential energy should not exist either, which means at infinite distance, when the distance between the two objects are at infinite distance, the amount of potential, gravitational potential, is actually zero. Now you might wonder, what is potential? We are talking about potential energy. What do we mean by gravitational potential? Gravitational potential has a definition, which I'm gonna tell you after a while. But before I tell you, I need to understand that at infinite distance there is no gravitational force. So because there is no gravitational force at infinite distance, the gravitational potential is zero. And now from the infinite distance, if we allow this gravitational pull between these two objects, I mean, if we allow the object to fall closer to the object, let's say if we allow this object to move towards the gravitational field, in that case, the distance between them are going to become smaller. The distances are going to become smaller. And whenever distance becomes smaller, the force of gravitation will work. So the potential will slowly become less. This is what I tried to show you right over here. I mean, look at for this part. Whenever we were working against the gravitational pull, we are storing energy, because we are moving the object from a higher potential region to a lower potential region. So that's why we had to do some work to make it move towards the lower potential region. So if the other thing had happened, let's say if we move the object from a higher location towards a lower location, then we don't have to actually push. The gravitational pull itself is going to make this motion. As a result, the object is going to lose gravitational potential energy, or we'll say that this is the object is going to lose gravitational potential energy and is going to move from a higher potential location towards a lower potential location. এই পয়েন্টের potential হবে কম, এই পয়েন্টের potential হবে বেশি, because it is automatically falling from higher potential to a lower potential value. However, if you want to move the object from a lower potential location towards a higher potential location, you have to do some physical work for that to achieve that. So if the object is allowed to move closer to Earth, it's going to slowly move from a higher potential region, which is really far apart, slowly to closer location, which means all of these points would have a lower potential. So as you slowly move further towards closer towards the Earth, your potential should slowly go down. এই লজিকটাই বুঝতেছো? The farther you are from the Earth's surface, or from the planet's surface, or from the object's surface, the more potential you have. So at infinite distance, your potential is maximum. But by logic, what is the potential at infinite distance? এই পয়েন্টের potential actually কত? The maximum value for gravitational potential is how much?
0.
0. So the closer you get towards the object, it is slowly becoming less than 0. So what is the likely values of gravitational potential at anywhere in this point? Which numbers are smaller than 0? Negative numbers, right? Think. So as we slowly get closer to the planet, the gravitational potential is going to slowly become less than 0. So we're going to have more and more negative number closer to the planet. For example, let's say we might have -1, we have -2, we have -3, maybe we have -1000, maybe we have -1,000,000. So 1, 2, 3, 4, 5, so I wrote 10 million over here. Anyway, the point that I'm trying to make is that by definition, the maximum gravitational potential is available at the farthest point from the object. By formula, because at the force of gravitational attraction at infinite distance is going to be 0. So the gravitational potential where it can be maximum at infinite distance will also be 0. Hear me out on this line once again. I'll say it again. The gravitational potential is logically, by definition, maximum at infinite distance, the farthest distance apart. By gravitational formula, reduced gravitational formula, the force of attraction at infinite distance happens to be 0. When there is no attraction whatsoever, obviously the potential will also be 0 because there is no force, so that there is no quotient of potential anymore because the force is not working. So it just so happens that gravitational potential is maximum at infinite distance, and the value of that maximum potential is 0. As we observe for closer points than infinite, it means as we slowly get closer to the object, the potential is going to decrease from its maximum value of 0. So potential will always slowly become more and more negative. Do you understand this idea?
Yes, sir.
Potential is such a quantity that will always be negative, and the reason it is actually proving out to be negative, because once again, like I told you, that gravitational force is a negative force. That's why gravitational potential is always negative, and it only has a maximum value of 0. It's sort of like the left side of the number line, sort of like that. If you try to visualize over here, this 0 is over here, and you only have on the minus side, on the left side of the potential. It's actually same everywhere. So close to the surface, you have the most negative potential value. As you slowly go farther away, it's going to become less negative, which means it's going to increase. And at infinite distance, it's going to become 0, which is the maximum value of gravitational potential. This is the conceptual dilemma which can bug you for some time. But anytime if you feel like remember this thing, you can go to the YouTube and have a look at this discussion. Or if you don't find that helpful or help you to remember, you can ask me. I'll try to make time and help you understand this again. But this is a concept that can prove too difficult to remember for many of the cases, and I know this for a fact. That's why I'm telling you this, to be careful about it. Now going for the bookish explanation of the formula, the textbook version. This is how that I can actually find out the notes and help you see it from there maybe. Oh, তোমাদের বুকলেট রেডি হয়েছে, তোমরা বুকলেট নিয়ে আসতে পারবা? সার্কুলার মোশনের নোটস কই? এসএইচএম এটা তো ইআরএমএস। হাই হাই। What? all right, so আচ্ছা এগুলো তোমার এক্সাম্পল গুলো তোমাদেরকে আমি এখনো পড়াই নাই, এক্সাম্পল আমি তোমাদেরকে পরে পড়াবো, গ্র্যাভিটেশনাল পার্টটুকু পড়ানোর পরে পড়াবো। এটা লাগবে আমাদের। একটা হচ্ছে হরাইজনাল সাইকেল, একটা হচ্ছে ভার্টিক্যাল সাইকেল, কোন সময় কি হয় না হয়, এগুলো কিছু হিসাবপত্র আছে। what I was trying to show you is the calculation for gravitational potential, এই যে এখানে আছে। So here it is. This is the definition, theoretical definition for gravitational potential. This is how it is defined. Energy required to move unit mass from infinite distance to any point of the gravitational field is the gravitational potential of that point. We are using the term energy required. It can be also said to be work done. Energy required and work done are similar stuff, so no big deal over there. So once again, have a try to understand the definition. Energy required to move unit mass from infinite distance to any point of the gravitational field is the gravitational potential of that point. The formula is given by phi equals to work done per mass. এখানে আবার আমরা w ইউজ করছি, এনার্জি যদি এখানে বলছি, so they are interconvertible. Let me draw this up for you for easier visualization. Let's say this is an object which is producing electric gravitational field around it, and let's say hypothetically, figure not drawn to scale, this is the infinite distance, and we have an object of 1 kg over here. So if we want to bring this 1 kg object from here to anywhere on the gravitational field around this object, let's say we are going to bring it right up over here. So in any path doesn't matter. I mean, you could go a long way, you can have overlapping paths, and eventually you reach to here. Path doesn't matter. If you bring an object from infinite distance to a certain point of this thing, and the amount of work that you have to do is, let's say, w to achieve this, in that case the potential of this point is given by w divided by 1 kg. If this had a mass of m kg, then this would have been w divided by m, or we could also write it as e divided by m. Sorry?
Because like it's getting closer to the field. Like, why would an external agent have to do the work? When a gravitational field, then yeah, infinite is a force zero no have but third normally feel that if you're moving closer to the mass, then the gravitational
Precisely.
bring it close.
Precisely. So we have said over here that energy required to move unit mass from infinite distance to any point of the gravitational field is the gravitational potential at that point. The idea is that if we are trying to move an object from an infinite distance to any point inside the gravitational field, the energy that will be required will be provided from within the field itself. We don't have to provide that energy. The gravitational field itself will do the energy. That's why in this case the work will be done by virtue of gravitational force, which you're going to see in the calculation now right after a while. I mean, this energy or work that we're talking about will be provided from the gravitational field itself, and that's exactly why the potential is decreasing. This is the high potential point, and to bring it from this point towards a point inside the gravitational field, we don't have to do any work. Any external agent doesn't have to provide any energy. The system itself will do it by its own virtue. What you said is absolutely correct, Ifat. So we're going to see about the derivation of this formula right over here. So we have some let me just minimize this one. Yeah, gives us a bit bigger view. So what it says is that, let's say we have a big mass over here, and this is the infinite distance. Let's say initially the object was at location B. The object has a mass of small m. Can you all see that, this figure? Hello?
জি স্যার দেখতে পাচ্ছি।
Awesome. So let's say this is this, and at this point, at this B position, let's say the force of gravitational force between the two objects is Fg. Now, because we are gonna go for some integration, and so that's why we're assuming that this object, by virtue of this gravitational force, is going to be pulled closer to the big object by a small distance of dr. But this distance BC is so small that we are considering that the Fg will remain practically unchanged. So for this small distance of BC, which is differential r, very small distance, the gravitational force will be effectively same. So we're going to consider that gravitational force to be pretty much the same. So have a look over here. Let, due to gravitational pull, m mass object moves by a very small distance dr towards m, then work done by Fg, work done by this gravitational force dw equals to Fg into dr. এটা মাল্টিপ্লিকেশন সাইন হওয়ার কথা, এখানে ভুলে এটা একটু বড় হয়ে গেছে. So work done is given by force into distance covered, Fg into dr. Fg is pulling that way, dr is going that way. So this is the actual work done by the gravitational field. Now, if we move the object from infinite distance to point B, if we move the object from infinite distance to point B, so আমরা যদি এইখান থেকে B পর্যন্ত মুভ করতে যাই, the upper limit is r equals to r, because this is the final position. Because whenever we are moving the object from infinite distance to B, we are starting from infinite distance and then we are finishing at r distance. So our starting value comes at the lower limit and our finishing value comes at the upper limit. So upper limit is r equals to 1, the lower limit is r equals to infinite. So we are placing those two limits over here and we're integrating the total amount of work done, that how much work would be required if we wanted to move the object from here to B. This was the differential equation based upon this idea, and then we are integrating from here infinite distance to B point. So we are placing the variables over here, fg into dr, fg equals to gmm by r square into dr. আচ্ছা, যারা এখনো ইন্টিগ্রেশন পড়ো নাই, ইন্টিগ্রেশন তোমরা ডেফিনেটলি পড়বা, ম্যাথসে পড়বা, আর যারা অলরেডি পড়ে ফেলছো তারা জানো এখানে কি হইতেছে। I am not so good with integration. I prefer to avoid integration as much as I can in places as I can. আমি ইন্টিগ্রেশন পারি, নিজের জন্য পারি, বাট পড়ানোর মতো ভালো পারি না। That's one thing that I'm gonna say. However, এখানে ইন্টিগ্রেশনটা করা হয়েছে, এখানে আমাদের জিও একটা কনস্ট্যান্ট, এমও একটা কনস্ট্যান্ট, স্মল এমও কনস্ট্যান্ট, সো উই আর টেকিং অল দ্য কনস্ট্যান্টস আউট। দ্য অনলি ভ্যারিয়েবল ইজ 1 বাই r স্কয়ার। 1 বাই r স্কয়ার কে ইন্ডিকেট করলে ইনটু এই জিনিসটা আসবে, মানে হচ্ছে এটা কেমনে জানি হয়, দাঁড়াও,
স্যার পাওয়ার প্লাস হয়,
পাওয়ার 1 প্লাস হয় আর নিচে হচ্ছে ওই পাওয়ারটাকে ডিভাইড হয়।
ওই রিজাল্টেন্ট পাওয়ারটাকে মানে মাল্টিপ্লাই করতে হয় উইথ দ্য,
আচ্ছা,
like you get 1 by r into -1 because the power is -1.
মানে হচ্ছে it all together becomes যে -1 into r to the power -2 plus 1, তাই তো? মানে something like this, I think. -2 plus 1 multiplied by r to the power -2 plus 1, এরকম না?
জি স্যার, yes.
এটাই তো, যে এখানে যেটা হবে ওটা দিয়ে সামনে আবার মাল্টিপ্লাই করতে হবে। I think so, as far as I remember. Anyway, so ইন্টিগ্রেট করলে এই জিনিসটা আসবে, এই জিনিসটা আসার পর আমরা হচ্ছে এখানে আমরা লিমিটগুলো বসাচ্ছি, খেয়াল করো। -1 by r, r infinity, so this is -1 by r minus bracket -1 by infinity, bracket close, so this is becoming -gmm by r. So ultimately এখানে এইটা হয়ে যাবে 0, আর এখানে একটা মাইনাস থাকতেছে, সো এখানে একটা মাইনাস আমাদের অটোমেটিক্যালি ওয়ার্ক ডানের ফর্মুলা চলে আসতেছে। Now you might wonder যে মাইনাসটা কেন আসছে, because like I said that in this case work is done by the system itself. So work is actually getting out, energy is given by the system itself. That's why the actual work done is considered to be negative. So potential at point B, phi of B point, a B point potential হবে হচ্ছে net work done divided by the mass, so phi equals to -gm by r. So এটা হচ্ছে আমাদের potential, gravitational potential এর basic formula. The minus will always be involved in the formula of gravitational potential, because like I said that why the minus is involved, because the value of potential will always be negative. And what is interesting for this expression, let me write this expression over here, phi equals to -gm by r, phi equals to -gm by r. What is interesting about this expression is that if you consider that, let's say here we have an object of mass m, and this actually tells us what is the value of potential in negative, as a negative number at a distance r from the object. So try to understand, this is the actual magnitude of this fraction. G is a constant, universal gravitational constant. For a specific object that we are considering, the mass of the object is also can be considered to be a constant. So capital M is also a constant. Now, if we do consider that we are going to consider the value of the gravitational potential at this point further out, you need to understand that if we are closer, this r will be small. As a result, the whole fraction will have a larger value. So you'll have a big negative number. If you slowly start to get further out, let's say you get further out, further and further out, so your total distance is getting bigger and bigger, your numerator will remain the same, but the denominator will slowly become big and even bigger. So the total value of the fraction will become smaller, which means you're going to have a magnitude wise smaller number, negative number, which means here you're going to have, let's say maybe a -1000, maybe you're going to have -500 over here, maybe you're going to have -200 over here. So the further out you're going to get, you're going to have a magnitude wise small negative number, which means the number is actually becoming larger in the general sense of numbers. I mean, a bigger negative number is small and a smaller negative number is large. So as you get further out, your number is slowly becoming larger, but it is only becoming less negative. And eventually, it is possible that at infinite distance, this number can become 0. Do you understand the significance of this minus value? এই এক্সাম্পলটা বুঝা গেছে?
Yes, sir.
Yes, sir.
আচ্ছা, এরপরে যে ইন্টারেস্টিং পার্টটা আসবে সেটা হচ্ছে আমরা কিভাবে জিপি ক্যালকুলেশন করব। সো delta gp, how do we calculate delta gp in our A2 level? Up until our AS level, sorry, O level, even AS level, we have always calculated change of gp is given by delta gp is given by m into g into delta h. এটা ছিল আমাদের কোর ফর্মুলা, mass into gravitational field strength into h. The only reason we could apply this formula because we always considered that delta h value to be of such small size that g could be considered to be unchanged. Let me elaborate this point. I'm going to draw a figure not drawn to scale, but try to understand. This is the earth. Here is the center of the earth. Let's say we have an object somewhere above the earth right over here, and we're going to move the object from here to here, right over here. Even if this figure was drawn to scale, this one distance is going to come into kilometers, but we don't usually do our math for kilometers. We consider an object is lifted by 10 meters or 20 meters into the ground and into the sky. What is the gp change? Anyway, what I'm trying to show you is that for near earth scenario, near earth surface scenario, the actual distance from the starting position to the center of the earth, let's say here the value of g is, let's say this is our r, exact r. So let's assume that the object was initially at ground. I would like to erase this. Okay, and yes, let's say the object was initially at ground and then it was lifted up by a value of h. Okay, so let's say at the ground value our g is equal to gm by r squared, and whenever it is at a height of h, at this location our g value should be gm divided by r plus h whole squared. If you wonder where is this coming from, this is coming from the gravitational field strength equation, which we just derived a little bit earlier. Where is that? There it is, g equals to gm by r squared. Have a look. This is the equation. R is the distance between the two objects, g is the gravitational field strength, gravitational universal gravitational constant g, capital G, and m is the mass of the field creating object. So in this case earth is the field creating object, so this is the position, this is the g value over here, this is g value over here. Now what I need you to understand, when h is really small compared to r, this g and this g, let's say this is g prime, I'm going to write that g and g prime are nearly equal. There is not much difference. So for near earth scenarios, for small distances, the value of g can be considered to be constant or same for both the starting position and also the final position. That's why this formula could be applied. But whenever you're going to start to move an object really far out, let's say you're going to move a satellite from the surface of the earth at a distance, let's say twice the radius. Let's say here the distance is r and here the distance is going to be 2r. So practically what you're doing, you are taking an object from a distance of r to a distance of 3r from the center to center distance would be in this case 3r. So in these scenarios, the value of g right over here and the value of g right over here would not be same anymore. So you cannot use this generic formula of mg into delta h anymore. You have to do your gravitational potential energy calculation differently because gravitational field strength is not remaining same anymore. Do you understand the logic?
Yes, sir.
I'll say it again. Because up until now we have always calculated the change of gravitational potential energy in near earth scenario for small distances, for small height changes, for such height changes where the gravitational field strength at the starting position and also at the ending position could be considered to be unchanged practically, for practical purposes. That's why mg delta h could be used. But for large enough movement cases, that whenever that g is not remaining same anymore, we cannot use this formula anymore. So what should we use? We use this formula. Delta gp is equals to change of potential multiplied by mass. So change of potential energy equals to mass multiplied by change of potential. If you remember, potential was defined by what? Work done per mass. So এটার ইউনিট হচ্ছে কি? জুল পার কেজি। আমি যদি ক্রস মাল্টিপ্লাই করে দিই তাহলে কি আসবে? Work done equals to কি আসবে? Phi into mass. So change of work done, or what we call change of energy, or what we can also say change of GPA, should be given as what? Change of potential multiplied by m. So that's basically how this formula comes into existence. That if you are trying to move the object from one potential point to another potential point, the amount of potential energy change is going to be the change of potential multiplied by the mass of the object. Now comes the idea that if we, whenever we are solving this, how can we write this? Let me just show you two scenarios. Let's say object over here, m, our test object small m was initially right over here. Let's say here the distance from center to center is, let's say, r1, and now we want to move the object from here to a farther away distance right over here. Let's say at the new position, the distance between the center to center is r2. So this is our final position, this is our initial position. So what you have to understand that can I accommodate this writing over here? I don't think so. এটা একটু নিচে নিয়ে আসি। Okay, so this can be written as করলাম So this can be change of potential can be written as final potential minus initial potential. I always prefer to write it in this fashion so that the students don't get confused that which one to use where. It's important that you do not mess it up because there is a built-in negative sign developed within the equation. It can prove to be confusing if you're not keeping the appropriate signs alongside. It can, not for everyone, not for every case, but sometimes it can be confusing. So I want all of you to make sure that sometimes does not happen in your actual exam. So final minus initial into mass. So এখানে আমরা যখন final potential এর ফর্মুলা হবে হচ্ছে minus gm divided by r2, because this is the final distance. We move the object from close to further away. This is the final, minus gm by r1. এটুকু হচ্ছে এই ফর্মুলা multiplied by small m. দেখো এই জিনিসটা বুঝা গেছে কিনা? I placed the final potential over here with the built-in minus sign of the formula. This minus sign is this one, and this is the initial potential with the minus sign and the initial distance r1. এখন এটাকে গুছাইলে eventually minus plus হয়ে gmm ক্যালকুলেট করলে একটা ডিফারেন্ট ফর্ম আসবে, সেটা হচ্ছে এটা থাকবে মাইনাস, এই দুটো মিলে প্লাস হয়ে যাবে। সো I can write gmm capital M and small m multiplied by 1 by r1 minus 1 by r2. So in the final expression you can see that 1 by r1 is coming in the front and 1 by r2 is coming in the back, but this is not because that we moved the object from r1 to r2. You have to understand that the object, I mean, this whole expression came from the mathematical outcome over here. Some people prefer to remember it like this just because they want to. I prefer to remember it from here, that we always do the final minus initial. That basically what gives us the value. It is also important for you to understand this expression in terms of mathematical term as well. Let me explain what that means. Try to think about it. If we are trying to move an object from this point to further out, who have to do the work? And does an external agent have to provide the work, or does the gravitational force itself will do the work?
External agent.
Correct. Pawan, bujo. We are trying to move the object away from the planet. So in this case, an external agent has to do the work, which means net work done is supposed to be positive. Because the system is not working, we are working against the system. So we're storing increased energy from an external agent. সো এখানে তুমি খেয়াল করো যে এখন যদি আমরা এই পুরো এক্সপ্রেশনটার ভ্যালু জাস্ট করি, হ্যাভ এ লুক, দিস ইজ 1/r1, r1 এর ভ্যালুটা হচ্ছে ছোট। সো এই ফ্র্যাকশনের অলটুগেদার ভ্যালু হবে লার্জ, এই ফ্র্যাকশনের অলটুগেদার ভ্যালু হবে স্মল। ডু ইউ এগ্রি অন দিস ওয়ান? Because r2 is a much bigger number, so 1/r2 would become a smaller value, and r1 is a smaller number, so 1/r1 will be a larger number. So the subtraction result of this whole thing is going to give you a positive value. So altogether the total product of this thing will become a positive energy, which means to move the object from this point to this point outwards, we're going to need positive energy, which means we have to do external work. External agent have to provide this energy into the system. Vice versa, if it was the other way around, if we are bringing an object from far out closer to the planet, then the outcome of this fraction, this bracket expression, would itself become negative, proving that we do not have to do any work from external agent. Rather, the system itself will do the movement, hence the work will be going out of the system. That's why the change of potential energy would become negative. এই আইডিয়াটা কি বুঝতেছো বলবান?
জি স্যার, বুঝেছি।
ঠিক আছে। সো এই জিনিসটা একটু কেয়ারফুলি ডিল করতে হয় যাতে করে এই জিনিসটা আমাদের ভুল না হয়। পরীক্ষায় খুব কমনলি স্টুডেন্টদের এই জিনিসটা গড়বড় হয়, সেটা হচ্ছে তারা এই জিনিসটা তাড়াহুড়া করতে গিয়ে এই দুটা মিসপ্লেস করে ফেলে, যে কোনখানে তারা এটা লিখবে কোনখানে লিখবে, কারণ দুটা ডিসটেন্স দেওয়া থাকে, এই দুটা মিসপ্লেস করে, এটা হচ্ছে একটা ভুল করে। আর এই ম্যাথগুলো করার আরেকটা ভুল করার লজিক্যাল, আরেকটা ভুল করার খুব কমন পয়েন্ট হচ্ছে যে এক্সামে ইচ্ছা করে এক্সামিনাররা যে কাজটা করে, ইচ্ছা করে বলতে দে অ্যাকচুয়ালি ট্রাইং আউট টু চেক ইওর অবজারভেশন পাওয়ার, that what they do is that they're going to give you the value of r over here, and they're going to give you the height by which it has moved from here to here. So these two values are going to be given. Let's say this is r, this is 2r. Now whenever you are trying to calculate the potential energy expression, you have to understand that the initial distance between from center to center was r, the final distance from center to center is actually 3r, not 2r. The object has gained a height of 2r from the surface. So how far is it from the center of the planet or center of Earth? That value is what? 3r. So in your calculation, your final distance should be 3r, your initial distance should be r, not 2r. Students are commonly just because they are not careful, that in many cases they use 2r as their final distance. 2r is not the final distance because the distances are measured from center to center. You gotta be careful about that fact. If numerical values are given over here, you have to add these two numbers to get the final distance from the center to center. Be careful about that. এটা খুব কমন একটা মানে ভুল করার লোকেশন যেখানে এই ম্যাথমেটিক্যাল ক্যালকুলেশন ভুল হয়। You're going to lose the answer mark only. You're not going to lose the theoretical mark or the method mark. But still, why should you lose even an answer mark? Because you know how to work out this mathematical problem, so you shouldn't. আচ্ছা, পটেনশিয়ালের গ্রাফের পরে আছে হচ্ছে আমাদের গ্রাফের কনসেপ্ট। গ্রাফ আমি আজকে তোমাদেরকে পড়াবো না, কারণ গ্রাফের পুরো কনসেপ্ট পড়াতে যথেষ্ট সময় লাগবে এবং গ্রাফগুলো আলাদা আলাদা করে পড়াতে হবে। টু বি অনেস্ট, গ্রাফগুলো অ্যাকচুয়ালি আচ্ছা না, গ্রাফ আজকে আমি পড়াবো না। কয়টা বাজে? 2:51। আচ্ছা, I'm going to close today's class, but on our next class, first I'm going to start with this one, object going in a horizontal circle, the conical pendulum. So I'm gonna talk about the horizontal circle, then I'm going to talk a little bit about the vertical circle. The vertical circle is not that much in your syllabus except for two exclusive positions. I'm going to talk about those, and then I'm going to talk to you about this example of banking angle for a certain vehicle when it's going around in turns, for example NASCAR racing or such kind of racings. And then we're going to talk about a little bit about aeroplanes as well. How does an aeroplane in air, atmospheric air, how does it turn using the idea of centripetal forces and everything, circular motion. It takes an arc, so it's a part of a circular motion. So we're going to talk about these stuff, and then I'm going to show you the graphs relevant to the two equations. One is gm by r square for the gravitational field strength, and the other one is gm by minus gm by r, that's for the gravitational potential. These are the topics we're going to pick up in our next class, which will be on Monday, 7:30 p.m.
Sir, actually about that, I have class till 8:30 on Monday.
আচ্ছা, গতদিনকে আমি 8:30 থেকে ক্লাস করতেছিলাম।
আমি তখন মানে ওই ক্লাসটা হাফ করে দেন I did your class.
Acha, I can actually start the Monday class from 8:30, but that would continue up to 10:30 if anyone doesn't have any problem, or if anyone is okay with that. I mean, it's a bit late, but I can do this up to 10:30 if it's like. তোমরা কি কেউ 10টার সময় ঘুমায় যায় এমন কেউ আছো? Like anyone?
না স্যার।
I hope not. So for convenience, I can actually shift the Monday class at 8:30. I have no problem with that. করা যাবে?
Thank you, sir.
আচ্ছা শোনো, Monday class যদি কারো প্রবলেম না হয়, we're gonna do at 8:30. I don't have any problem with that. আর হচ্ছে এই বাকি ক্লাসে হাফ আওয়ার প্রবলেম নেই। আমি ইয়ার সাথে ওর নাম যেন কি ভুলে গেছি,
Sadia.
সাদিয়া, হ্যাঁ সাদিয়ার সাথে আমি পরে আবার আলাপ করে নিব। থ্যাংক ইউ ভেরি মাচ। আমি একটু পরে লেকচার আপলোড করে দিচ্ছি, আর গ্রাফগুলো নিয়ে নেক্সট ক্লাসে ইনশাআল্লাহ আলাপ করব। আসসালামু আলাইকুম।